So when we did the activity in class, we observed a pattern, right? And for instance, for f of x equals x to the fourth, using the limit definition of the derivative, our expression ended up being the coefficient, the exponent became the coefficient, and our exponent ended up being reduced by 1. And this is known as the power rule. Okay? And you might wonder, well, why did we do all that hard work with the limit definition? Well, the power rule is just a pattern that occurs from the limit definition, which and so something you should know, and it's true not only in math but in every area of life, is that if you don't really understand where something comes from and you don't really understand how it derived, you don't really understand the concept. It becomes just a dog and pony show. It's almost like you can do a trick. You don't know why you're doing that trick. You don't know how that trick relates to anything else, but you can do that trick. And so I'm very, very careful not to teach you just a bunch of tricks, because if that's the way you learn, your learning ends up being very, very shallow, and you've got really no foundation whatsoever. Everything you're going to find out in calculus goes right back to the limit, right? Every single concept. And that's actually a crucial, crucial understanding. Right? So you don't really know calculus if you can't apply limits to solve a problem. Right? So using our limit definition, and we'll go back and forth to that limit definition for derivatives, and we'll be using limits for other things as well. But we can also use power rule as a shortcut so long as we understand the mathematics behind the power rule. Right? So our power rule, so d dx stands for take the derivative. Right? So if you take the derivative of a variable raised to a power, right, your derivative is going to end up being, using the limit definition, that power is going to end up being the exponent, and your exponent is going to be reduced by 1. So the rule states that the derivative of x raised to a power is the power times x raised to a power 1 less, or n minus 1. Right? And I will have you go back and forth between them, but we'll often use our shortcut now that you understand where it comes from. Right? So our derivative here would be 8x to the 7th. Right? And that's how you apply that rule. It really comes in handy when we have more complicated exponents to raise something to a power to. Right? So if something's raised to the 100th power, right, that might get awful tedious using the limit definition. Right? But then we could use the power rule, as long as you understand where it comes from. So here's a little proof, and I'll use an example just to help you out. Right? So d dx means take the derivative of x to the nth. Right? So if we're using our limit definition, as h approaches 0, x plus h to the nth power minus x to the nth power divided by h. Right? And that's just our limit of the difference quotient. Right? And when we expand, we raise to the power, we would end up with x to the nth. Right? So the first term raised to that power plus, right? And then that n is going to be, our exponent is going to be a coefficient, and each time your exponent is going down by 1 power, your x is going, the x term is going down by 1, and the h term is going up by 1 until you get to the very end, right? And h is now to the nth power, and then you would just you'd be subtracting that function. So let me just give you a concrete example just to help you out. So the limit of, and we'll use x cubed, right? So we're going to take the derivative. Actually, let me give myself a little bit more space here. I'm going to take the derivative of x cubed, right? So that'd be the limit as h approaches 0, right, of x plus h cubed minus x cubed, cube is getting a little closer to the parentheses there, all divided by h. Right? And then we would expand it out, so we have the limit as h approaches 0. Right? And so x plus h cubed is x cubed, the first one cubed, plus, and then it's going to be 3 x squared h plus 3x h squared plus h cubed minus x cubed, all divided by h. And so let me just move this over a little bit. And so now if you look over to your right there, let's move that over a little bit, and you see that's what you can see right here. Right? Notice that matches. Right? And that's going to be the pattern all the time. Right? And so then when we simplify, right, we would cancel out the x cubes. Right? So we'd have the limit as h approaches 0. We'd have 3x squared h plus 3x h squared plus h cubed all over h. Right? And that's what we have here in this step. Right? So you notice everybody's got h's. And then you would factor out that h. So you have the limit as h approaches 0. Factor out the h. You've got a 3x squared plus 3xh plus h squared, all divided by h. The h's would cancel. All right, and then once you plugged in 0 for the h's, you'd be left with the limit as, I'll write this part down. The limit as h approaches 0. You'd have 3x squared, and then everything else has an h. So plus 3xh, and then plus h squared. Right? And as soon as you plug in a 0 for h, these would go to 0, and that's going to leave just 3x squared as our derivative. Right? And so that pattern keeps occurring over and over again. Right? And so when we recognize the pattern, we can use that pattern to help us find derivatives more quickly. But the important thing is that you understand the pattern and you understand where it comes from. All right? Otherwise, you really don't understand what you're doing. And we want to make sure, I want to make sure that you understand what you're doing. All right, so let's take a look at this one. All right, so we'll let f of x equal 1 divided by a, right? And we have our limit definition. Right? It's already set up for us. Right? All right, so we need to get a common denominator there. So that would be the limit as h approaches 0. Our least common denominator is going to be a times a plus h. The product of those, because they don't have anything in common. All right, so we'll have a times 1. I'll put the 1 there. And divided by a times a plus h. And then minus, and then it's a good idea to do plus and negative, so you don't forget to distribute the negative sign there. Right? And that's going to be 1 times, right? So that one has an a, so it needs an a plus h. And then we have both terms with a times a plus h as their denominator, and then of course divided by a. And then we would distribute our negative sign. We'll distribute the negative and clean that up and make that one fraction. So we have the limit as h approaches 0. It's going to be a. I don't need to put 1a there. So I'm going to have minus a minus h, right, when I distribute the negative sign. And then the denominator, we have a times a plus h divided by h. So now let's clean that up and combine our like terms. We have the limit as h approaches 0. And a minus a, of course, is just going to leave the negative h. And then I have a times a plus h. And let's automatically rewrite that as opposed to divided by h as times the reciprocal. And that makes it nice and super easy to cancel out. All right, always make that times the reciprocal. And so now we have the limit as h approaches 0. We've got negative 1 divided by a times a plus h. All right, and so now we can plug in. All right, so our derivative, because we know we were taking the derivative, f prime of x, we're going to plug in the 0 there, so we're going to have negative 1 times a plus 0. Of course, that's just negative 1 times a squared. Right, and that's our derivative there. My a is starting to look like a 9. Let me just clean that up, make that a little bit nicer. Let's take a look and use our power rule and see what we get. All right, so now there's our derivative using the limit definition. Let's use the power rule and see what we get. So we have, if I use the power rule, I need to rewrite, first of all, f of x. So f of x equals So that would be the same as a to the negative 1, right? Because power rule doesn't deal with rational functions, right? It only deals with variables raised to a power. So f of x equals a to the negative 1. If I want to use that power rule, right, that exponent moves in front, right, and I reduce the exponent by 1. So I'd have negative 1 minus 1. Well, negative 1 minus 1 is just negative 2. So we have negative a to the negative 2 power. And we could simplify that. Simplify that negative exponent. We'll always simplify the negative exponent to negative 1 divided by a squared. And notice that's what we got, except for some reason I dropped the negative. That's what we got when we use the limit definition. All I had to do was copy it and copy my negative in there. All right? So the power rule also applies to negative exponents. So everything we do here I'm going to prove out for you first. So like I said, if you don't understand where formulas and things are derived from, then you don't really understand the formula and you don't really understand how to use it properly. All right, so power rule for negative exponents. All right, so if I have 1 over x, that's equal to x to the negative 1, right? Or x to, and so let's find our derivative here. Oh, shoot, we already did that on the other page. All right, so I don't really need to do this one. I just did that one on the other page. Whoop, let's do this one. All right, so we have 1 over x squared. So if f of x equals 1 over x squared, which is the same as x to the negative 2, our derivative is going to be negative 2, okay, come on, times x to the negative 3, and we'll simplify that, and that would be negative 2 divided by x cubed. Right, and likewise, let's get rid of all that, and we'll just rewrite it again. All right, so if I have f of x equals, we'll get rid of this one too. Since I rewrote it much nicer, we'll just move everybody over. There they come. All right, so if f of x equals, well, we'll use 1 over x to the 7th. Actually, we don't even have to have a 1, but I'll leave it as 1 right now. F of x equals 1 over x to the 7th. All right, so that would be the same as x to the negative 7. And if we take the derivative, f prime of x, the negative 7 would move in front, so we have negative 7 times x, and then we'd have negative 7 minus 1, and I really should have done that over here, really, just so that you got the idea. Here, I'll redo that for you. For now, anyway. There we go. For now, I'm going to make sure I show every single step, right, so it makes sense to you. Right, and so now we could rewrite that as, I'll write down here, f prime of x equals negative 7 times x to the negative 8, and of course we'll simplify that. All right, so that means f prime of x equals negative 7 times x divided by x to the 8th. All right, so there's our power rule for negative exponents. Constant multiple rule, so scalar. So the rule states that the derivative of a constant times a, the derivative of a constant a times a function is the constant times the derivative of the function. All right. So power rule, if we have x to the 5th, right, the derivative would be 5x to the 4th. Let's say we have a power rule and a constant multiple. So let's say we have 7x to the 5th, right, and that's right over here. If we have 7x to the 5th, right, we're going to take the derivative of, we're going to take 7 times the derivative of x to the 5th, right? And so the derivative of x to the 5th, of course, is 5x to the 4th. And so 7 times 5x to the 4th is going to give us 35x to the 4th. Right? So when we use the difference quotient, so we're going to take a look at that. When we use the difference quotient, we're going to look at it one more time though. We observed that since the limit had no effect on a constant coefficient, the constant can be factored on the outside. And we'll look at a problem like that. I think I have it all done on the next page. So just a little vocabulary there for you. D dx means that to differentiate or take the derivative with respect to x. Dy dx is the derivative of y with respect to x. So d dx is a verb, dy dx is a noun. All right, so let's look at that, prove that scalar, and then we'll do some more with the scalar. All right, so here I did leave this one out. All right, so here we have the limit as, and I'll just use my handy dandy arrow. This one I didn't rewrite. And actually, it looks really nice. That's probably why I didn't rewrite it. I'm so impressed with my handwriting. So we had the limit of 7 times x plus h squared minus 7x squared. Right? So we're finding the derivative of 7x squared. Right? And so we could factor that 7 out. Right? So we got to factor out of both of them. Right? So you didn't have to distribute it. You could factor the 7 out. You didn't even know that, did you? Of course, and that only works when everybody's got a 7. So if I throw anything else in there, well, that would mess that up. But we factor the 7 out. All right, so now we have 7 times the limit of x plus h squared minus x squared. All right, when we expand here, we have 7 times the limit of, as h approaches 0, of x squared plus 2xh plus h squared minus x squared. The x squareds are going to cancel. Right? And so then we have 2xh plus h squared divided by h. We'll factor out the h there. And so now we have 7 times the limit as h approaches 0 of 2x plus h. If you plug in 0 for h, you've got 7 times 2x, which is 14x. All right, and that's the same thing you would get here using the power rule. So f of x equals 7x squared. All right, the 2 moves in front. Now you've got 2 times 7, right, which is 14, and you reduce the exponent by 1. All right, so if you have a scalar multiple, you just multiply your derivative by that scalar multiple, whether you're using the limit of the difference quotient, or whether you're using the power rule. The same thing would occur. 7 difference rules, and actually we've been using those all along. I just didn't give it a name. So this rule states that the derivative of a sum or difference is the sum or difference of the derivative. Right? So when we had a sum or difference and we used the limit quotient, we just found the limit basically of each one, right? Because the sum of limits is just the limit of the sum, right? So we didn't have to reconfine it all together. All right, so here if you want to take the derivative of u plus v, you just take the derivative of u and you take the derivative of v and add them together. All right, so if we have y equals x to the 4th plus 12x, right? Using the power rule, the 4 would move in front. We reduce the exponent by 1. Right, so that would be 4x cubed. And then do the same thing with 12x. Right, so technically the 1 moves in front. So you've got 12 times 1, which is still 12. And then you reduce the exponent by 1. So that makes it x to the 0. But x to the 0 is just 1. Right, so our derivative would be 4x cubed plus 12. Right, so you just add those terms together. Right, you just take the derivative of each one. Here we have y equals x to the 4th minus 2x squared plus 2. Right, using the power rule, the 4 moves in front. We have 4x, and we reduce the exponent by 1. So we have 4x cubed minus, right? And so now we've got, this would be a constant multiple rule right here. Right? So now you've got 2 times 2x to the 2 minus 1 power. All right, so that would give you 2 times 2 would be 4, and then you have x to the 1st. That gives you 4x. The derivative of a constant is just 0, and we learned that earlier in class. All right, so we want to find the horizontal tangents of y equals x to the 4th minus 2x squared plus 2. So horizontal tangents occur when the slope is 0. Right? The slope of a horizontal line is 0. Slope of a horizontal line equals 0. All right, so we're going to take that derivative because the derivative gives us slope of the tangent line. All I put lines because there's many. There's an infinite number, depending on which point you decide that you want to use. All right, so here our derivative dy dx. Right? So that's the derivative of y, by the way. So derivative of y is dy dx. That'll come into play later on. All right, so x to the fourth, derivative of x to the fourth is going to be 4x cubed. Derivative of negative 2x squared is going to be negative 4x. And the derivative of 2 is just 0. Right, so that gets dropped. All right, so now we want to know when the slope is 0. All right, so we're going to set our derivative equal to 0. All right, we're going to set dy dx equal to 0. So we have 0 equals 4x cubed minus 4x. So now we'll factor that. We could factor out a 4x. That's going to give us x squared minus 1. Right? And we could factor x squared minus 1. So we've got 4x times x minus 1 times x plus 1. Right? So that gives us 3 solutions. So 4x equals 0, x minus 1 equals 0, x plus 1 equals 0. So x equals 0, 1, negative 1. All right, so that's where, our horizontal tangents occur. It's said to find the horizontal tangents of. Right, so this is where the horizontal tangents occur. Right, substituting the x value back into the original equation, you can find the y values. All right, so if we plug in the 0, right, so f of 0, that'd give us 0 to the fourth minus 2 times 0 squared plus 2. Of course, that's just going to be 2. F of 1, 1 to the fourth minus 2 times 1 squared plus 2. All right, so that's going to be 1, I'll write it out, 1 minus 2 plus 2, so that's just 1, and then negative 1. And so f of negative 1 would be negative 1 to the fourth, and then minus 2 times negative 1 squared plus 2, and that's just going to be 1 minus 1 plus 2 plus 2. Excuse me, 1 minus 2 plus 2. Right, because the negative 1 would be squared, so that'd be positive. So that again is going to be 1. This is a very, very symmetric function. All right, so those are our I'm running out of space here. Those are the y values for those points. I don't know if I gave myself any space on the next page. If not, I'm going to expand this page. Oops. Let's see if I gave myself space on the next page. Nope, but I went over it. All right, so, but let me, with a graph. All right, so let me just do that. All right, so that's, we wanted to find the horizontal tangents. All right, we found where they occur. All right, so we have a horizontal tangent at 0, 2, at 1, 1, and at negative 1, 1. If we wanted to write the equations, right, we'd have y minus 2 equals, what's our slope? Well, 0 times x minus 0. So I hope you see that that's going to be y equals 2. And you probably figured out that the other ones, if not, here I'll write it out, y minus 1 equals 0 times x minus 1. Hey, it's y equals 1. Right? And so we're going to have 2 of those y equals 1s. Right? Those are our equations, right, for our horizontal tangent lines. Right? And we have one occurring at 0, 2, one occurring at 1, 1, and one of them occurring at negative 1, 1. Right? Same equation, it's just in 2 places. All right, so let's take a look at this graph. All right, so before we do that, let me just recap here what we did. All right, so you're asked to find horizontal tangents. All right, you're asked to find where they occur. Right, you need to set your derivative equal to 0 because derivative equals slope. Right, and you want to know where that slope is 0. And then if you want to find where so that's where they occur, that's half of where they occur. The other half of where they occur are the y values, right? The y values, that comes from the original function. So y values are original function. They're the y values. Okay, and then the slopes, that's your derivative. All right, so let's take a look at this graph. All right, so our first derivative or slope is 0 at y equals 0, -1, and 1. Right? So when x equals -1, the slope of the tangent line is 0. All right, so we've got 1 right here. Boop. And then again, when x equals 0, our slope of our tangent line is 0, right? So, right, and we have 1 at 1. All right, so here's the other one. And then, when x equals 0, the slope of the tangent line is 0. Well, that's odd. If we look at our original function, it doesn't look like we have a horizontal tangent there at 0, right? So how do we get 0? Oh, excuse me. This isn't our... So sorry, so sorry. Should probably cut that out. I stood here for a second, then I looked at the function. That's not our original function. This is the graph of the derivative. Oh, silly, silly me. I forgot. I put the graph of the derivative here. So the graph of the derivative. I'm looking at these and I'm like, doesn't seem like that's at 0, 1. It's not. This is the graph of the derivative. I'm allowed to make one mistake when it's late. All right, so on the graph, the graph of the original function, it's going to look kind of like this, right? Ooh, like a W, right? It's x to the 4th, right? The graph of our derivative, right, is going to be 1 less. It's going to be cubic, right? So if f of x is x to the 4th something, f prime of x is going to be x cubed something, right? So this is the graph of the derivative. This is where the derivative equals 0. If we had our original function, which I don't think I have on the next page, it'd be nice. Do I have the... No. I don't have the original function, but let's kind of sort of graph it out. All right, so it's going to kind of look like this. All right, not quite exactly. All right, and now you can see, right? And when we're 0, it's 2. All right, so it's not really drawing to scale per se. All right, but now you can see that our tangent lines would be horizontal on our original function. Those correspond to x-intercepts on our derivative. Right? So horizontal tangent lines on f of x equal x-intercepts on f prime of x. So it's good I let you think there for a moment. Because then you're realizing it doesn't look like x to the 4th. I've got it. What's graphed is 4x cubed minus 4x, our derivative. I forgot I had done that. All right, so where we have x-intercepts on our derivative, those are horizontal tangent lines on our original function. All right, and so you might wonder what these horizontal tangent lines on the derivative, what these are. Well, you'll have to wait for that because we're not there yet. But one day you will learn what those mean and how they relate back to the original function. Anyway, this is a good place for me to stop, and so I will. In the next podcast, we're going to look at radical functions and finding their derivatives. All right, and then we're going to learn some more rules that will help us. All right, bye for now.